All right, why don't we hang on here a minute while I check out. Okay, that's fine. Why don't we take up where we left off? But first, administrative notices. The next homework, which is due at the end of this week, is up. And I think I corrected the incorrect dates and things on it by now, but in any case, it's due this Friday. So we offset the date because there was a slight delay in getting it out. The Project 2 is out, and the TAs will be meeting with teams. I don't know if it's starting today. Well, there will be meetings today and then throughout this week. Please make sure that you show up for these. We want to make sure that the teams are operating. If there are any more team adjustments that I have to know about, please email us. Do not use Piazza for requesting team changes. It is not the appropriate medium, as I have said many times. And unfortunately, it turns out that GitHub Classroom is not quite as flexible as I had thought in doing this sort of stuff. So we will be, so when you have to change a team, there will be some kludging necessary, but it'll be all right. It should work out. You should have access to everything. I will also be posting some sort of a poll, well, a sheet for people to make sure that we are on the same page when it comes to who is on what team and who has what login and so forth, because unfortunately, for the same reason, I have a few difficulties with GitHub Classroom getting it to do the right thing. So we'll keep a separate log so that we know exactly who is doing what. Okay, questions, issues before we start. This is where we left off last time, and we've just gotten to the point where we have a language implementation in which there is a desire to have what are called, what were called in, for example, Algol 68, local generators, things that would generate local variables on the fly. So normally, you have a Java program, you have a function in C, Java, C++. The local variables are those that you declare, and that's it. And the idea is to generate new ones, or at least new local space, I should say, on the fly, that, like other local variables, goes away when you exit from the function. And this is a way to carry that out without disrupting the mantra, if you will, the property that everything that the compiler, everything that you have to get to in a subprogram is at some fixed offset from some known register, which is always a good idea, which makes the code sequences faster. So the compromise is to say, okay, fine. Well, this extra on-the-fly storage, being of variable sizes, will have to be referred to by a pointer, but there will only be a fixed number of pointers because you only have a fixed number of things that you're referring to that way, just as for any Java program. And the only difference will be that we will put these so-called unboxed structures on the local stack here. And we'll sort of pretend, we'll sort of make, the compiler will sort of wave its hands so that you don't actually know that there's a pointer involved. That's sort of the idea. And the way that you bring that about is that you simply put it on the stack like this. You have a fixed location local pointer that points to it. You get as many of these as you want, and it all works out fine. And then when the function returns, you go back to where you came from. But the effect on the implementation is that you now need this, you now can't just use a stack pointer to get at things. you also need a frame pointer because the location relative to the stack pointer of all of this stuff down here, all your local pointers and so forth, is now no longer fixed. It might vary depending on how your program executes, what new data you generate. And therefore, in order to have something from which there is a fixed offset to all these things, we absolutely need a frame pointer. Frame pointers are useful for other purposes as well, but this is one that makes them absolutely necessary. So it's an example of a sort of a language feature that makes a necessary change in the underlying representation, in parts of the representation that perhaps don't seem to be directly related to that feature. All right, so this is basically the idea behind the basic procedure calls, such as you would find in C and C++. You have a stack that contains local storage and also contains local storage. It contains saved registers, in particular the return address, plus a link taking you down to the preceding stack frame so that you can restore the frame pointer when you return. So the return sequence involves, first of all, when you return, you want to return the stack to the state it was in, well, aside from function results and so forth, to the state it was in before you called, which means you want the stack, when I return from this guy here, I want the top of stack to go back down to here, and I want the frame pointer to go back down to here. Well, getting the stack down to here is very easy because I have this frame pointer, which is at a fixed distance from where the old top of stack was, so I just move it. And then restoring the frame pointer, however, since we assume that when I'm compiling this program up here, or this function, I don't necessarily know anything about the function that I'm being called from. Therefore, I need this pointer here to get back there in general. The dynamic link, or control link, as it is called in some of the literature. So I hope that all is clear. If not, now's your time to complain, because we're going to add another level of complexity next. Okay, good. You're ready for more complexity. Great. Well, let's see what we've got here. Well, as you know, in Python, you can have nested functions. So I can have a function here nested inside a function here. And the question becomes, okay, fine, just exactly how do I get at this, how do I get at the information in the function outside me, the function I am nested inside? And this is especially problematic when I have something like this. Here's a recursive function, which means that at the time that I finally get around to asking for y, which is a local variable in f, this nested function out here, there might be any number of these frames for g, in between where my top of stack is, and where my frame pointer is, and where f is, where y resides. Y will reside presumably somewhere down here. So how do I deal with that? Not only is the distance not fixed, but I don't even know. I can get down here by following dynamic links. It's true, but I don't even know how many dynamic links to go down. It could differ depending on how the program execution has gone. So the question is, how do we deal with this situation? And the answer is that we go back to basically CS61A again. in a disguised form. So in 61A, you remember that we had environment diagrams. And one of the things in environment diagrams is that environment frames had parent frames. And this is how that appears in something like C or C++, and how we can do it in Python. So here is what we'll do. We'll have that situation that I had before, where I had a bunch of G frames and then an F frame. So we'll have the G frames. Their dynamic links will go like this. In other words, every frame will point to the frame before it on the call stack. And in addition, every time we call G, we will pass an extra parameter. So the regular parameters to G will go here, right, just before the G's frame. So for example, when F calls G, it will build up a bunch of parameters here and then call G, and then G will be able to get at those parameters. In addition, however, we will also pass to G a so-called static link, which is the address of the frame of the function that encloses G. So when I, F, call G, I will tell it that, oh, by the way, your local variables are that any local variables that you get from an F, they come from here. They come from my frame. So it will have a pointer down here to its own frame. And each G, when it calls G, it will say, well, I see that you are me. You're the same function as I am. Therefore, you are going to need to get your non-local variables from the same place I do. So I will just pass up as your static link, this same value, this same static link. So all of these G frames have the same parent frame, namely this F. Now you should recognize this from CS61A. Heaven knows we give you enough of those exercises in that class. So this is exactly what's going on, but at the machine code level. So now, if I have to get at a variable down here in F, when I'm way up here in G, I just say, okay, well, F is the function that immediately encloses me. So I should be able to look at my static link and find that variable in F. So I will go down here to my 0th parameter, if you will, and voila, there it is. And that's pointing to where I should find that non-local variable. So far, so good? How many people remember this from 61A? Just 1? 2? 2.5? Okay, folks. We all understand that we have to present this material many times before it sinks in, because people, when we present it the first time, people think, oh, that's the last time I'm ever going to see this, so as soon as the exam is over, I will forget it. Wrong. That's not how science works. Okay, we actually do stand on the shoulders of giants. We build on work that we've done before. So this is an example of that. So just to make this really concrete, let's take a look at how this translates into risk 5. Oh, I'm sorry. I forgot to say that if you go back to the slides from last time, you'll find that I have made a couple of corrections, and you'll see them here also in some of the code sequences that I did. Okay, so here we are. So here is our function over here on the left, and you can see that we have a function f0. Inside it is nested f1 and g1, and inside f1 we have f2. then when we call F0, it will call F1, F1 will call F2, and F2 we'll call G. So, how does this work? Well, first of all, let's just look at F0. F0 doesn't have really very much to do. We'll ignore the fact that F0 is at the outer level, and therefore we don't actually need a frame pointer. Oh, and I should also say that I'm using C notation, even though C does not officially have, or maybe it does by now, I don't remember, but this is GNU C, which does allow nesting. And this is not, in fact, the implementation that the GNU people actually use. Is everyone familiar with the acronym GNU? Who is not? You've never heard it before. Okay. Do you know what it stands for? Yeah, it's precursor. What does it stand for? Yes? Right. GNU is not Unix. Since now Linux is officially GNU Linux, this doesn't make any sense. But no, you'd have to meet Stallman to really understand this, it's quite an experience. All right, so this is what we have. So we'll take the frame pointer, and we're going to store it. Since the stack pointer on this machine, we're always having it point at the next empty location on the stack, the one sort of above the top of the last thing pushed on the stack. So we will save the frame pointer and then the return address on the stack, and then adjust the stack pointer to make room so that the stack now encompasses these two things that we've pushed, plus also some room for S, for this local variable here. Now this is actually would in some cases be a dicey code sequence, by the way, just so you know, because I am saving things on positions sort of above the top of the stack before I've moved the stack pointer. And normally you'd think, well, that shouldn't make any difference, but imagine what happens if you're in the midst of doing this and all of a sudden in comes flying an asynchronous interrupt. That is, something happens, like an I/O event. And in which case, the operating system will do something that vaguely resembles a function call to whatever handler you have for that interrupt. And that could erase what you've just put on the stack. So, but the RISC-V people have a convention that says that there's a certain area above the top of the stack of limited size that is guaranteed not to be disturbed until is guaranteed not to be disturbed. Period. In the normal course of events. So I'm simply taking advantage of this. All right. So we push these two things on the stack. They correspond to the FP and RA that on the preceding diagram. We adjust the stack pointer, and then we do the usual thing. So I want to I set the frame pointer now relative to the stack pointer. So I'll skip I will skip to the location of the pushed RA address, return address. And now I will start looking at, I will start picking things up. So I want, for example, N0. Well, N0 is the first parameter. If we look at how this is done, if the frame pointer is pointing here at RA, actually here up at the top of RA, remember the addresses are going negative or going down in this direction, up in this direction. So so that means that N0, the first parameter, the first and only parameter, is going to be here. It's going to be at offset 8 from the from the frame pointer. So I load that in. I negate it by subtracting it from 0. For those who you have seen, they did do RISC-V in 61C, did they not? If not, you can Google the RISC-V instruction set. Instruction sets are quite similar. There'll be conventions for any given machine, and then you understand it. So this is store word, add immediate, load word, subtract, and 0 is a register that always contains 0, sort of wired to 0. So I subtract, this means subtract this operand from this operand, giving this operand, so I get -0. Then having done that, we will store that in S. S is, with the conventions that I'm using here, S is at address, it's above the return address on the frame pointer. That is, it's right in here, for example. So that's in a negative direction from the address here of RA. So I do that, and then in order to call F1, I have to pass it its static link. Now F1 is nested inside F0. Therefore, its static link is simply going to be my frame pointer. So I save that in the location into the location of the first or the 0th argument to F1. Then what am I calling with? I'm calling it with 10. Then I get the argument 10. I create the argument 10, load immediate. And I store it in the argument, the next argument after the stack pointer. Adjust the stack, and then jump to frame 1. So I will have the stack pointer. I will have the static link to frame 0, and then the argument 10 on the stack, and I will call F1. This is not necessarily the best code sequence, but we'll use it anyway. So I will then return the stack to where it was before the call. I will return the stack pointer to where it was before the call of F0 by adding 4 to it. And then I will restore RA and FP and jump back to the return address. All right. So these are load word, add immediate, and this is jump to register. Jump and link, jump to register. Okay, any questions about this code sequence? I think it's pretty straightforward. Okay, so now let's see how we do other things. Here's F1. Now in F1, we have to access N0, and we also have to call F2. When we call F2, we have to save its static link, which is the static link of, since F2 is nested inside F1, it's the static link of F1. So we simply store F1's, FP is now F1's static link. We store that where we did before as the first argument. And there aren't any other arguments, so we simply call F2 at that point. Now to get at N0, we first take the static link that we were given, which is at 12 off the FP. In other words, it's the argument before, and it's the argument, is it 12 off the FP? Hang on. Yes, I think that's right. 12 off the FP, the one before N0. The one before N1, excuse me, the one before N1. And then from that gives me the address of F0's frame, and from that I now load F0, or S. I now load S, which is in here. Oh, N0. Excuse me. I load N0, which is the first argument to F0. So I do that from using my static link. Now down here, all right, then and then I do all the return stuff. There's a little interesting glitch here in that in order to do this absolutely correctly according to, well, I'm using C here, so I actually, in the case of C, this is an interesting point. I've taken the trouble to pull out N0 here and then save it on the stack, as you'll see. So I've taken N0, I've saved it on the stack before calling F2. Now, in the C language, I don't actually have to do that because C does not define the order in which two operands like this, N0 and F2, are evaluated. So in C, I could instead have called F2 first and then fetched N0. Then I would not have had to save N0 on the stack over the call to F2. In Python, however, which is what we're doing, in Python it is defined that you evaluate the arguments left, the operands, all other things being equal, you evaluate the operands left to right. And of a particular operation, you evaluate them left to right. And so in that case, to be absolutely correct, in Python, I do have to store it like this. So that's actually an interesting difference. Now, in fact, most C compilers, or I'm sorry, at least the GNU C compiler, generally tend to evaluate their arguments backwards, from right to left, in a function call, from right to left instead of left to right, which might seem a little bit strange. But in fact, the reason for that is they use that freedom because it happens to be convenient. The convention in C, unlike the convention we're using here, is that the first argument goes closest to the top of the stack, whereas we're using the reverse for historical reasons. Or rather, my predecessors used the reverse, so I'm doing that too. So in C, they tend to put the argument, a lot of these implementations do it that way. And the reason is, if you think about it, that means that I can push the arguments on the stack in order, so that they are in the proper order on the stack, by evaluating the right one first, pushing it on the stack, the second to the right, and pushing it on the stack. That way I evaluate the first argument, the closest to the top, last. So it goes closest to the top of the stack. So that's an interesting thing. That feature of C, the fact that you have this sponginess in evaluation order, simplifies some of their code sequences, and also speeds up, I should say, some of their code sequences. So it sounds like a minor thing in the language, but it isn't necessarily. Now, it's also somewhat of an infernal nuisance. I think maybe once or twice in my career, I have actually encountered a case where it makes a difference which way you go, left to right or right to left. So when you consider that that's 50 years, all right, maybe I shouldn't have admitted that, but anyway, it's something like that, roughly, from high school. That tells you that kind of error is not all that common. It gets a lot of attention in the academic research literature because this simple little thing has profound effects on how you describe the semantics of the programming language. But for most programmers, it's a big, meh sort of thing. And the reason for this is that you don't usually write function calls that are so complicated that you've got multiple side effects in the arguments, so that it matters what order, and there are multiple related side effects so that it matters what order you do it. You don't do that very often because that's an obscure program. So it's an interesting little, just a little interesting sidelight, I think. Okay, here's F2. Now F2 is the most buried one. So we have the usual stuff to start with. We don't actually need to do any of this because F2 doesn't call, well, oh, I'm sorry, yes we do, because it calls it G1, sorry. So now how do we get at S? S is an N0, which are way out here. Well, we have to get, we take my static link, which is a parameter to me, to F2. That gives me the static link of F1. Then in order to get to F0, I take F1's static link, and that gets me to the frame for F0. So that's what that code sequence is about. All of the rest is straightforward after that. You just realize you have to follow the link twice to get back out there. So it's not really anything mysterious going on, but you're basically following the parent chain in the environments twice to get back to N0. And then off we go. Now, you notice that as you can see, in order to generate this code, I have to know, I'm taking advantage of the fact that the compiler, while it's compiling this, knows all about F1 and F0. These are not, because nested functions have this property, that if you're nested inside somebody, typically, the compiler has complete information about what those things that you're nested inside look like. In other words, it knows what your callers look like. And therefore, it's able to do this kind of, it's able to know exactly what fixed offsets to put in these loads and stores. Whereas if you're being called from outside, you don't know what the frames of your callers look like. But you don't need to because you're not nested inside them. Therefore, you're not allowed to get at any of their variables. Anyway, so you never need to do that. Finally, we have G1, and G1, we can, did I do it? So I've set up a static link and so forth for G1. And G1 is nested immediately inside F0. So when it gets S, it simply has to access its static link. So we load, and now I'm going to, since G does not call anything, it's a leaf procedure as we call it, I won't even bother to store I won't even bother to set up a frame pointer or to store the return address. I don't need either one of them. I can use the more primitive calling sequence that I did before, and there do everything relative to the stack. So I pick up I will then pick up my static link, which is my only argument, since G1 has no other arguments, and I will load S from that and then return it. So there you have a complete nested function and the way that it accesses things. So that's it. That's CS61A's environment diagrams now translated into machine language. And so these stack frames correspond to environment frames. And all's well. Okay, well now, interestingly enough, things weren't always done this way. As you know, I mean, when you look at those static links, what you see is that you've got a linked list of environments, of environment frames, of stack frames. Environment frames if we're talking 61A, stack frames if we're talking this class or 61C. But of course, a linked list is just a kind of sequence, and sequences can be represented with arrays. And in fact, arrays were the way the way that was originally proposed to do this. I believe this is a suggestion from Dijkstra way back in the late 50s, early 60s, of how you would deal with this nested function problem in the language at that time, the interesting language at that time, which was Algol 60. So he had a different idea, and that was that we look at we make use of the following observation. If I am in a function that is not nested inside any other function, I will say that I am at lexical level 0. If I'm nested inside a function, I will be at lexical level 1, and so forth. At any given time, assuming that we're just using the features that we've seen so far, at any given time, the only functions to which I have access, whose variables I will need, are functions whose lexical level will be either me, or functions whose lexical level is less than mine. So here, this guy, F2, will need access to the functions at level 1, F1 functions, and the functions at level 0, and his own local variables, but he doesn't need access to the local variables of G2 or anything like that. He doesn't need this other sibling local function. Furthermore, if there's been a recursion of any kind, so that, for example, G2 is called F2 or something like that, or it's called itself recursively, it will only need access to the latest G2 or to the latest level 1 procedure. And I will never need, and in here, I will never need access to this other functions, even though this is a function at level 1, I don't need access to his variables. There's only one level 1 function to whose variables I need access at any given time. So there's only one level 1 function to whose variables I need access inside G2 or F2. And furthermore, there is only one stack frame for that function in the case of recursion that I need, namely the latest one. And these facts together say that we can do things like this. As we build up our frames, say F0 calls G1, for example, we will store off here to the side in an array that's called the display, which is a kind of an odd name. You might say display. That's the thing I look at when I type. Well, you have to understand that this term was invented in the early 60s, before there were displays. So there you go, right? That's history. That's history for you. Okay, so I will keep track of what the current stack frame is at level 0, at lexical level 0, what the current stack frame is at lexical level 1, and so forth, in an array that's indexed by lexical level. So at any given time, that's where the latest thing will go. Now, when G calls F1, at this point, the frame at level 1 will be F1. I won't, in doing this, I had to overwrite the G1 that used to be there. But that doesn't matter because F1 can't look at G1's variables, nor can anything nested inside F1 look at G1's variables. Nor can F1 call a function that's nested inside, nor can it call a function that's nested inside G1. There aren't any here, but there could be. it can't call that because the function inside G1 is local to G1, so it can't call that. So there's no need, so at this point, there's no need for G1's frame while I'm executing F1. F1 now calls, F1 calls F1 again, and again, all I need is F1's latest frame, because neither F1 nor anything nested inside it can get at this F1 frame. There's no way of, the language doesn't give you a way of talking about the variable x inside the recursive instance of F1 that happened 3 times ago. There's no way of saying that even. So F1 can call F2. Now F2 is at level 2, so we enter a new thing into display. And then G2 is also at level 2, so we change the F2 frame to G2 frame, and so forth. And finally, we go back to G2 eventually comes around to calling G1 at some point. When it does that, it will, G1 will set the level 1 frame to its frame. And you'll notice that there is now still a G2 frame here, so which would, in principle, allow G1 to look at G2's variables, except that the compiler doesn't let you say that. In the programming language, you can't say that anyway. You can't say, if there happens to be a G2 executing at the moment, give me its variables. You can't do that. There's no way of saying that in the programming language. So the fact that this G2 is sitting here while I'm executing G1, that's irrelevant. It doesn't matter. Now when I return from G1, I go back to G2, and you notice that when I do that, I have to restore this pointer to what it was before. So before the call, this was F1, and after the call to G1, this has to go back to an F1 frame, which means that it is the responsibility of G1, when it's called, to save the old value of display 1 and restore it when it returns. And so we continue in this fashion, going back down and restoring both the display pointers and so forth as we go along. Oops, I was going, well, yes, this illustrates that in fact I can go in either direction and it gives me the same effect. So how do we do this? Well, this just means that when we're in a function of, say, level 0, the first thing we do, this is the regular stuff that we do, frame pointer, dynamic link, return address, and dynamic link. And we, then what we're going to do is we leave some space for a bunch of stuff, S, R, A, S, L, and also the old value of display 0. We get our F0's frame pointer, and we first of all get the old display 0 and save it on our own stack. We store our frame pointer in display 0, and then we carry on. F1, same thing, except that we take the old display 1 and we substitute our own thing for display 1. You notice the display sub 1 here, the first item is at address display plus 4, assuming that we're using 32-bit addresses. So in other words, every time we enter a procedure at level X, at level N, we save on our own stack the old value of display sub N, and we push our own frame pointer into display N. Now, when we are inside F2 down here, and we want to access N0, we pick up, instead of following the chain of things, we can pick it up directly. So in other words, if we didn't have to look at anything inside F1, unfortunately we do in this case, but if we didn't have to look at anything inside F1, we could simply pick up F0's static link directly. We don't have to follow a chain of things. It doesn't matter how deeply we're nested. And we then pick up the N0 from that. It's the same thing. So this is kind of neat. And it means that it avoids because it's an array, we don't, and if we have deeply nested functions, it won't matter. It'll work just fine. Of course, the thing is that you don't have deeply nested functions very often, so it doesn't make all that much of a difference. On the other hand, another thing that this does is if you're a function that doesn't call anything underneath you, doesn't have any nested functions, you don't have to touch the display at all because it's never going to matter, which is kind of a nice feature. All right. Well, so far we haven't provided for function values. We're like Chocopi. It does not allow a value to be a function. But Python, of course, does, and so did Scheme, allow you to have functions as values. And it introduces a new problem because a function, because you don't know when you call a function that's a parameter, you have no idea whether, you have no idea at that point just where anything is. You don't know how to get at that function's static link or anything like that. You have no idea where that function parameter is coming from. So it's different from what we've been doing so far. That means that a function has to be more, unlike C, where there are no, in plain C, where there are no functions, where there are no nested functions, we have to carry a little more information with each function value. And in fact, that's exactly what happened in 61A. Right? So in 61A, when you represented a function, there would be two things. There would be a pointer to the code for the function, to the implementation of the function, and there would be a pointer to that function value's parent, the frame in which it was created. You had both of those things. So that's what we'll do. We will have a function value for G. I've happened to put it off here on the side on the heap, although that is necessary. That isn't actually necessary in this case because we are going to assume what I call proper nesting. In other words, we will never call a function. Unless that function has been defined in a frame up on the stack somewhere. But as you may recall, in 61A, we did more than that. Okay, well, before I continue with this, rather than chop this off in the middle, I think that we will stop at this point, and I will finish up all of this material on Wednesday. Okay, I will see you then.